that we're going to deviate from the original plan to be even more auxiliary to Nikita's lecture, so I'm going to just kind of explain some of the things that he wanted to explain, I guess. So maybe, sure. Where's the chalk? It's on the other side of the board. All right. Okay. This will last us a while. So maybe we'll start with this localization thing. So maybe the first time you see it, or the first time you see it, you think, wow, this is amazing. But then maybe, no, it isn't. So, and yesterday we had this heated discussion about who thought about it first, and of course, you know. But the truth is, in equivariant K-theory, people knew this forever. And in fact, so this goes back to the questions, like if I have an infinite dimensional, so this goes back to the old question. Suppose I have a, you know, like maybe G is a compact group, say compact Lie group, and I have an infinite dimensional representation of this group. Maybe I take like, you know, L2 on G. Right, so it doesn't, so if an infinite dimensional space, it doesn't, the character of an operator is not going to make sense, generally speaking. But it was understood long time ago by Gelfand and, I don't know, maybe Harishchandra in the West, that the character is actually, so the way to think about the character is a distribution. So maybe V is some infinite dimensional representation, e.g. this. V representation may be infinite dimensional, so e.g. regular representation. So then the character of V, is, you know, may not be able to compute it on an element of the group. It's really distribution. So if I have a phi which is sufficiently nice, phi, or maybe phi is a sufficiently nice function, I don't know, maybe C infinity compactly supported function on my group G. I mean, okay. No need to compactly support it since it's compact. So I already made this assumption. So then the value, so then I want to pair K with phi. Well, what is it going to be? It's just going to be the trace of I take, instead of taking an operator, so I'm going to integrate over the group, I'll take an average value of an operator. So I'll take an action in the representation Tg. So this is probability Haar measure. Haar. This is operator. And the point is that this is an operator which we cannot take trace. If you average, this will be a trace class operator, you can take a trace. Okay? For instance, so in the adjoint representation, what is it going to, in the regular representation, what's it going to be? In the regular representation, this operator, so maybe I'll write, I'll just write this maybe more. So I'll define kind of like the trace. So maybe this is the pairing of my character with the function phi, and this would be by definition the trace. I'll call this operator. Okay, this is the pairing of chi v and phi, and this operator here, maybe I'll denote pv of phi. Makes sense? so what is this guy in the joint representation? In the regular representation. In the regular representation, this is an integral operator. Because in the regular representation, you just act by translations on the group. So it's an integral operator. Integral operator. In fact, that is to say an operator of the form that you have a function. If you have, so you have a function here, and you apply your value by v phi applied to the function f. So it's a function. We want to compute it at some point g. So that's an integral operator, means an integral over the group G. There's some kernel k gh f of h dh. And what is this kernel? The kernel is just phi of gh inverse. Right, this is how this operator acts in regular representation. And so a kernel, what does it mean a kernel? Kernel is like an infinite dimensional analog of a matrix. It's some function. It's some function on the product of G with itself. So if G is finite, which is a particular case of compact, then this is like a matrix of the size G times G. Otherwise, it's a function on G cross G. And you apply this function. So this is my kernel kgh. Well, what it really is, it's kind of a tuplet operator. It means it's a constant on the sort of diagonals. On this diagonal, it takes, so if there's an element, it's the element G and an element H, and it just takes value f gh inverse. And you apply these operators, you would apply matrix. Means how do you apply matrix? You multiply and you sum. And so except your summation is continuous here. And so then what's the trace of this matrix? Well, I mean the trace, it's clear what there should be the trace. The trace is just then the integral. The trace is the integral over g k of gg. dg, but that's just phi of 0, right? Because that's phi of 1 rather. Right? Because this on the diagonal is a constant function, and we normalized it to be probability measure, so you get just this because it's the one and the same value in the diagonal. So the moral is that the character of the regular representation is a distribution, and the distribution supported at a single point is a delta function at the origin. Right? And so then if you're interested in more interesting characters, if you're interested in characters like fine dimensional representation and some other representation that have more interesting characters, they'll be given by some function, maybe locally integrable function on your group. And then as you compute this function, you can neglect anything of this kind. This is the kind of localization computation where you're interested in a function or some object that you want to know almost everywhere on your group. And in this computation, you're free to neglect anything that is supported on. This is kind of the, so this is in the language of we used yesterday, this is torsion. Right? This is actually, so this is a distribution that's actually killed by multiplication by a function. It's like killed by multiplication by any function that vanishes at the identity of the group. And we'll do some kind of more down-to-earth computation in a second. But since I already have this formula, I wrote this intentionally. Is that you have? Remember when? Yesterday we spoke about that, like, in geometry we have whatever manifolds and maps between them, but in physics we want to have vector spaces and like operators. And that we talked about like a vector space could be, for example, equivalent K-theory of some manifold X. And then the operator, what was the natural operator? The natural operators, they are the exactly same kind. So there's if I have So analogy, so this may be, like I say, convolution operator. Convolution. Or correspondences. In K-theory, this is called correspondence. Correspondences. In K-theory. So the same kind of picture, you have maybe two spaces, doesn't have the space to itself, maybe X and Y. And you have a K-theory class on the product, which I'll just maybe denote K. This is a K, well, maybe this is too much. Maybe I'll denote it A, or whatever, B, or C, or whatever. Phi, oh, phi goes 9. So if I have a K-theory class on the product, then there's an operator. Then phi defines an operator from K-theory of Y to the K-theory of X by the exact same formula. If I want to apply phi to a vector, let's say you have a vector bundle with sheaf on Y, so maybe there's some sheaf. There's some sheaf. Oh, okay, didn't have to went that far to get another green. So let's see. This is red. So there is some sheaf.
What's the point? The plotting
So the trace of an integral operator, I mean, it's very easy to imagine what's it going to be. You can approximate any integral operator by an operator of finite rank. Just make it so make it like a locally constant operator. Then clearly for a finite rank, there'll be just a sum of diagonal eigenvalues, and that sum will approximate the integral.
No, I mean, your pair though.
Yeah.
Doesn't depend on the representation.
It is in the regular representation. I compute in the regular, so right in the regular representation. Yeah. So this is if I have a sheaf F here, then what I can do is I have a projection to Y, maybe call it Py, and I have projection to X, Px. Then if I want to apply this operator to F, what I do is I pull back it to phi, to the product. Well, you pull it back to the product, then you multiply it by phi, and you push it forward here. That's exactly what you do with functions. With functions, you pull it back to the product, you multiply it by some function on the product, the kernel, and you push forward means integrate. Anytime you have to do these operations with any kind of, if you have any functor from spaces to vector space, from topological space to vector spaces that has pullbacks, push forwards, you have operator like that. And that's how things act in K-theory. I mean, you should remember that, of course, when you pull object back in K-theory, you have to resolve it by vector bundle. When you push object forward in K-theory, you have to compute all the push forward is not just global sections. You take sections minus first cohomology plus second cohomology, you take the Euler characteristic. But that's the one and the same formula. We'll come back to that in a second. But let's now, using the fact that the regular representation of a compact Lie group is a distribution supported at identity. It's a delta function at identity. Then let's just redo the fact that we do like the first example of localization theorem. And suppose I have a covariant vector bundle on P1. So suppose I have my P1. So P1 has a point 0 and a point infinity. And suppose I have an action. Maybe I'll denote an element of this by Q, if I may be forgiven. And so I have a covariant vector bundle. In particular, it has some fiber over 0, so maybe I'll just denote V0. And it has some fiber over infinity. I'll just denote V infinity. And then, so what does it mean? What does it mean I have the covariant vector bundle means the action on the base is lifted to the action on the fiber. So Q acts here too, and there's somehow acts there. Yeah, they're fixed points, yeah. And so now I want to know what is the character of sections of this guy, right? Oh, sorry, cohomology of this. Right? So how do you compute cohomology? I take an open cover. There is a cover, maybe I'll write U0, which is P1 minus infinity. This is the neighborhood of 0. There is a cover U infinity, which is there's a chart U infinity, minus 0, and there's this intersection. Maybe that's their intersection. Right. And so then I look at sections. So in algebraic geometry, when people talk sections, they write the word gamma. They anticipate the fact that the character of something like this will be given by gamma functions. So you take sections on 0 plus sections on U infinity, and there's a map that takes section here, section there to their difference, and there will be a section of restriction on this U0 infinity. Okay. There's a takes you know, this if a section is 1, maybe S0, and then there's S infinity, and this map takes us to S0 minus S infinity. So the kernel of this map are the global sections. Kernel here are the sections that are, so if you have sections on the whole thing, it's the section here, section there, that glue on the overlap, that is say in the kernel of this map. And the co-kernel of this map, that's H1 by definition. Okay. And so if I want to compute the character of H0 minus H1, I might as well compute the character of this plus the character of this minus the character of that. But now this, I claim, this here is a copy of regular representation. I mean, some number of copies. Some number of copies of regular representation. Right? Because why? Because here is the here's the coordinate. There's a multiplication. I have a function named with the coordinate. Just maybe I'll call this function z. This function is not 0 nor infinity. It's an invertible. So this is z is an invertible function. Function of non-zero weight. In fact, non-trivial weight. In fact, kind of defining weight. Right? This is Q acts on Z by defining representation. And so multiplication by this function, it's an operator that is an invertible operator that just makes this representation have a bunch of copies of regular representation. So the character of this guy is torsion in every sense of the word, right? Like if I take meaning this representation here in the sense of analytic sense, we just discussed, that's the delta function and the identity of the group. In algebraic geometry, this space, so this multiplication by Z, if you think of gamma, there is multiplication by Z to the same guy shifted by kind of 1. I mean, equivalently shifted kind of tensor whatever Q. It just says this, maybe I'll just write times Q. Okay? Okay. So this says it's an invertible map. So it means it's an invertible map. There's no kernel, no co-kernel. And the map takes this representation to representation shifted by Q. So that says to say this representation times 1 minus Q is 0. If you have a representation such that this equal, if you have a character is equal, the equal times Q. So this my 1 minus Q is 0, which is consistent with the fact that this character is really a multiple of the delta function at Q equals 1. Q is my element in the group. So this is torsion, we can just forget about it. And in general, if you have an algebraic variety with a torus action, you can cover it by charts such that only the, so the abstraction to having an invertible function of non-zero weight is actually have a fixed point. And so you can cover it by chart such that you have fixed points in the first chart, no fixed points in the rest. And so then the rest contributes nothing, because you can further cover it by charts that each has an invertible function. But the actual theorem will already state that the actual theorem in K-theory is this localization theory that talks about actual K-theory, not global sections, but it's somehow it's. And then what are the characters here? Well, my vector bundle is going to be trivial, since it's a covariant vector bundle. It's going to be trivial on this neighborhood of this, and trivial on the neighborhood of that. And so what will be the character? The character would be it's a trivial bundle. I mean, it means function some number of times. So this is restricted to no. This is like gamma of this equal to the fact the same thing I take just the fiber V0 tensor polynomials in my variable z. Actually, if you somehow, I told you very important to distinguish between representation and dual representation. Strictly speaking, z has weight -1. Is that q -1? Is that okay? Because it's a function. So if I'm defining, so if q is the weight of the actual action, then it acts on the function. If you want to move the graph of the function left, if you want to move the graph of the function one way, then you have to in fact subtract the argument. So on function it acts in the opposite way. So this means the character there is just the trace is whatever it is, the trace of q in V0 divide times the character here, but the character in this polynomials is just 1 minus q inverse. Right? Because what are the polynomials? Are there's 1, z squared, and so forth. There's a geometric series that sums up to this. Okay? So what we've proven is that the trace, I want to compute the trace of q on h0 of v minus h1 of v of the element q. This is equal to the trace of well, I guess I wrote it the other way around. Let's just keep q in mind and take the trace on h0 minus h1 of v. This is the same as the trace on the fiber over 0 over 1 minus q inverse plus the trace of the fiber at infinity over 1 minus q. It's 1 minus q because at infinity, instead of polynomials in z, you get polynomials in 1 over z. So this is the special case of the formula we somehow stated last time. You can check because so in general, if I have, so last time what did I say? I said if I have this localization in K-theory, what does it say? It says that if I have any element v in K-theory of variety, so there's this it's equal to what? To the push forward from the fixed locus. I'll just write the kind of restriction to the fixed locus. You take sum over all fixed locus. You take components f of the fixed locus. So this is an element in covariant K-theory of some manifold X. So I look at all components. I restrict V to that component. This is the analog of this. And I multiply by, or rather I divide by the exterior algebra of the cotangent space, or sorry, conormal space. This kind of alternating serial algebra, maybe I'll write with the minus here. You take you take the normal space to X and F, and I take the dual. Okay. Here in this example, the normal space to X in 0 in this example is a representation of my group is just Q. And so when I take and then I take exterior algebra, means I take 1 minus L1 plus L plus L2 and so forth. So so this expression becomes 1 minus the dual. So the dual, that's Q inverse. Dual means you take all the variables. So how does a group act in the dual representation? It acts by transpose inverse. The transpose doesn't change the eigenvalues, but inverse does, and namely takes all elements in the group to their inverses. And so this is example of that here. Okay. And so an exercise, which is so I'm going to be there'll be no new batch of exercises. An exercise is to do the wild character formula from this perspective. So we haven't done this exercise. It's a very good exercise. So if I take X to be G mod B, then if I take a one-dimensional representation of B, so we discussed that if I have this makes X a B bundle. I mean, this gives you a particular B bundle over X, namely G. And so if I have any representation of B, I can have an associated line bundle. If I take one-dimensional representation, I have a line bundle for any character of B. And then you compute the Euler. So this is if maybe lambda is a character of B, and then there's a associated line bundle. And then you compute the Euler characteristic of this. This is the wild character. So Raoul Bott derived it like this. Must have been late 50s. I was long before any heated discussions that we had yesterday. I was long way before that. So this is Bott's proof of. Right, it requires a Cohomology vanishing, but that Cohomology vanishing is this guy, for dominant weight, this guy is ample, and so then it's somehow okay. Right. So now what does this? What is the common feature of this? I mean, this is an example of wild character formula, in fact, and that's another instance of wild. I mean, so what's wild character formula? Wild character formula. Everybody knows what's a wild character formula? Yeah, the formula. Yeah. Anybody? So what does it say? It says a character of a finite dimensional representation, which is some Laurent polynomial in variables, is given to you as a rational function. So this in a computation like this, there's always a little bit of a miracle that you write a finite dimensional representation or finite dimensional virtual representation as an alternating sum of infinite dimensional representation. And so then of course the guys we discard localizations means we discard all those pieces that come from charts that don't have fixed points in them. So we just their characters are all torsion, and so whatever. But then there are pieces that have fixed points in them. They're rational functions by the argument, by generalization of this argument, and then it becomes a miracle that you have a rational function that in fact equals a polynomial. In fact, that means all poles in this function, they just cancel. And you can write many important equations in mathematics and mathematical physics as the fact that you start with something which you thought is a rational function, but in fact it's a polynomial. And in fact, the subject of this school, and I'm very happy that Nikita came here, is about exactly this type of relations. Is that when you write some, so you have some integral, well, integral in this case maybe sum, and you integrate in the integral sign. You plug in a rational function. And so you think that if you integrate a rational function, the result should be also a rational function, or worse. But in fact, it comes out the all poles cancel. And that is proven, well, I guess we'll get it to the end by the end of the week. This is proven exactly this way. So that you interpret this as a computation of some Euler characteristic on something which is, how do we know ahead of time that something is in fact Laurent polynomial? If it's this, you have to, there's some compactness argument, or properness algebraic geometry says. So there's something which is in fact compact. You do this, you compute it, and so it should give you a finite, it should give you something without poles. And then you compute it by localization, you get something which is a priori looks like it has poles, but in fact it doesn't. And that's a very non-trivial constraint. And in fact, so to my mind, there are many applications like this in mathematics, and to my mind, there's no better tool in all of mathematics to prove that poles in some expression cancel as to interpret that expression as a result of localization of something. There are many. Right. So now we're going to finish. We want to finish the discussion, this correspondence, since I have it on the board. And I stated the following kind of important theorem, and maybe I'll build an illustration to using this. So there's the following theorem of, there's many names, but the end result is by McGurty and Nevis. That K, the topological K theory of Nakajima variety, X Nakajima variety, algebraic, this is the same, generated by, so you can say it's either generated by the tautological vector bundles in the sense of lambda rings, but if you want in the sense of usual rings, then it means you have to take all the exterior powers of tautological bundles. So the K theory is a ring in which there are extra operations, there are the exterior powers. And so then if you, in the sense of ordinary rings is this. And then, and the same, similarly, if you take the cohomology, is generated by the analogs of that in the ordinary cohomology. These are in fact, integral cohomology. This is generated by this ith exterior power of the tautological bundle becomes the ith Chern class of the tautological bundle. Tautological bundle. No, I mean this is probably something else. So it's tautological bundles mean tautological bundles on Nakajima variety. And so how this is, so what's the main idea of the proof? And the main idea of the proof I'm going to explain with something which is strictly speaking not a Nakajima variety. And in fact, so for that manifold, the issues that in fact were resolved by McGurty and Evans, they don't arise, but I'll just explain nonetheless. So let's take Grassmannian. Let's take instead take X to be actual Grassmannian, not the cotangent bundle. course, for cotangent bundle, we have general statements that all that stuff for the total space of the bundle is the same on the base. So let's take just take Grassmann. So it means over X we have the so maybe I'll write it like this. X is the Grassmannian of K-planes in n-dimensional space. Over that, we have so there's a point here. So a point here is a vector subspace. Maybe I'll write it L of dimension K inside Cn. And so over that, I have my tautological bundle, L itself. And so now let's look at X cross X. So this is cross, this is another X. And so over another X, so maybe I'll just write L1. And so this sits L1, and then there sits a bundle, which is its L2. And then I have, over this product, I have a tautological map. I have a map from home, I have an element, tautological element in home from L1 to the quotient of Cn by L2. Namely here, what do? I take L1. It's by definition embedded in Cn. And then I can project to Cn mod L2. X is just Grassmannian. And that is another X, another copy of the same X. So this says over, so maybe saying over this product, there's a tautological section of the home from this to Cn mod L2. And we had some colored chalk somewhere. No. This is L1 is a point, and this is a point called L2. That makes sense? That helps. So then there is a canonical map. Where does this guy vanish? It vanished exactly. This map, maybe call it S. S is 0 exactly when L1 is equal to L2. So that everybody's agrees with that. So S is 0. This is equivalent to L1 equals L2. So means S0 cuts out exactly the diagonal. The diagonal is something of codimension. Codimension is equal to the dimension of X, which the dimension of Grassmannian is K times n minus K. And that's exactly the rank of this bundle of homes. The homes, this is K dimensional. This is n minus K dimensional, so it's exactly the bundle of homes. So diagonal is exactly cut out as a section of a map between tautological vector bundles. And so that means the diagonal has as an operator. So among all possible operators, we have if x equals y, then there's a when x equals y, then there's a very special cycle here. There's just diagonal. And so this is the graph of, if you think about a graph of like a matrix, that's the identity matrix. And in fact, it's pretty clear that this operator is really the identity map. Right? And so that says that if I have a resolution of diagonal by tautological bundles, then what do I have? That means I can write the identity map like when same thing when you write this, when we did this functional analysis at the top of the hour, we were thinking about in this kind of functional analysis story, we had some operator k of xy, but people also like to write it as some summation of whatever fi of x, gi of y. Expanded in some kind of basis of functions that pull back from here, pull back from there. So if I have the solution of diagonal by a section of topological line bound, then that means the identity operator means if I can write the diagonal, I can write as the sum of whatever alpha I tensor beta j, where this the beta I, where this is pulled back from this is some, sorry, maybe I'll write it like this. This is some expression in L1 is a K-theory class, and this is some expression in L2. And I wrote this tensor for emphasis. I write some expression in L1 and L2, and I just write and expand it out. I'll get sum of terms which want something called 1 times something in L2. And so then when I apply this operator, what I'm going to get? When I apply this operator to a function, what I'm going to get? I'm going to get the k applied to some function, whatever psi, that is summation over I, and this is evaluated at x. This is summation over fi of x times the integral of gi of y psi of y dy. Says that the image of this operator, this says the image of this operator is spanned by this function fi. Okay, clear? This is like take a matrix and write it as a decomposition of something of rank 1, and then whatever you get here, that's what the image is spanned by. And so then that says that the image of this operator, which is image of the identity operator, is spanned by expression in L1, which is what we wanted to prove. Do you have a question?
So we have sort of just alpha I minus beta I so far in your resolution, but isn't that when you continue the resolution or something, you see some products?
Right. No, but what does it mean? You want to have something, something suppose you have a subvariety written as a vanishing of a section of regular section of a vector bundle. Then this means this structure shift of the subvariety is given by the Kazul complex, which we discussed it last morning, and Nikita discussed it again. So it just means you have means you have a Kazul complex on L1 tensor this guy, and then this says that well every exterior power of the tensor product of two shaft chain can be expanded into some expression that involves just them separately. I mean, the actual terms here may be kind of complicated, but the conclusion is that if it only uses organic ingredients, then the product is organic. That's the type of argument. There's no contamination by other classes. You're not going to get any other class. So then, what? Well, because you will take wedge powers of some home from here to here, right? It just means it's just some. All you say, you have some abstract symmetric function, some bunch of variables, and all you know, it only knows that you have a symmetric function in some set of variables and some other set of variables. You can expand it, like the elementary symmetric function being the generators of the algebra symmetric function. You can expand it in this form. That's all it says. Right? The calculation with exterior powers, right? Maybe that's important. The calculations with vector bundles are the calculations with symmetric functions, in which you assign to a bundle a bunch of variables, which are called Chern roots of that bundle. And then when you take the tensor product, these variables multiply somehow in all possible ways. And then if you take the direct sum, you just take the unions of these variables. And if you take exterior products, you take elementary symmetric functions in these variables, and so on and so forth. And so the only thing we really need is that if I have some symmetric function of symmetric function of k variables, which are the Chern roots of this guy, and k different variables, which are Chern roots of that guy, then any expression of this form, I can expand the symmetric function of one times symmetric function of that. Okay. So, right. So now I promised Nikita I'll do fixed points. And then, right. So what about the general Nakajima variety? For general Nakajima variety, there's something kind of amazing. So there's a similar thing. Right. Where does this proof breaks for Nakajima varieties? The proof breaks for Nakajima varieties because Nakajima varieties are, strictly speaking, not compact. So when you push forward, you have to. You can only push forward if there's some conditional support your class, which these classes don't satisfy. When you have a vector bundle, that doesn't work like that. So the proof of McGurty and Evans is to compactify the situation and use. So you put like you somehow add something at infinity to make things work. Right. So these Nakajima varieties are kind of amazing in that you think, well, maybe I'll just say a word why they're amazing. Is by definition. So this is just maybe just a word of. We'll come back to this later. They're really well. You think, well, maybe it's not so. How can this be useful? It really is useful, in the sense that you should really think of this as a moduli of representations of a certain algebra. And what is this algebra? That's just algebra. That's just the algebra of really kind of the path algebra of your quiver. So it means this is, you think of this as an element in the algebra. And then namely this is path algebra of quiver. Modular relations that come from the moment map. Okay? You think, well, how can this be useful? But in fact, it's super useful because this is how you prove that in fact there are no strictly semi-stable points. Because if you have some general quotient you don't know, but for representations of algebras, you, for example, know that there's this is very useful. And also this gives you something like, if you think about how you compute the tangent, like the computations of like the tangent. I don't know if you guys did this example already. When you compute the tangent bundle, then you did you compute the tangent bundle to Nakajima variety? Okay, cool. So what does it look like? So there's the tangent bundle. You take the actual tangent bundle of this framed representation, the cotangent bundle to this framed representations. Then there is a map from here, the derivative of the moment map. This is how you impose equations. So it means you impose the moment map equation. So the tangent bundle to this, strictly speaking, Okay, now it's a linear space, so its own tangent. So you have this linear space. So this goes to where? This goes to direct sum over vertices. You take GL of V, I, well, kind of dual, if you want to be concrete. Okay. And then there's a map which is just the action. Take the direct sum of GL VI. This is just the action. And so that to compute the tangent space, you need to take the kernel of this map and mod out by the image of this map. Okay. But if I tell you these are in fact modular of representation, really fine moduli spaces, that this tells you more, because the tangent, well, what's tangent bundle? Tangent bundle to representation is x1 from representation to itself. So this term really computes, this is just really x1 term, and the cohomology of that term and the cohomology of that term is the x0, well, just the home from some representation to my representation to itself, maybe R, and then this is the home from R to R. The cohomology in all these terms, and this is the x2. Yeah, we'll come back to that. But then there is, based on this, you can write the resolution of diagonal for any Nakajima variety. Because the same kind of argument, that if you look at the representation in the same degree, then there's no room for homes unless they're guys exactly equal. And suppose you have two representations of the algebra with the same dimension. So if they're both stable, there's no room for homes, unless they're exactly equal. And because stable means it doesn't have subrepresentation of a certain kind, and then there's using the sequence you can write. In fact, this sequence is going to come up in the definition of Y operators. I think this is why I wrote it down too. But anyway, something like this gives you resolution of diagonal for any Nakajima variety. Maybe I don't have time to that, but then this is how this is the beginning of the argument, and then you need this McGurton-Evans type of quantification, which I'm not going to explain. Okay. And maybe one point I want to make is that if you think of Nakajima variety as moduli of objects in some category, you really don't need to think of that category concretely in terms of what it really is. Like with instanton moduli spaces, you can think of them. The instanton moduli space is a concrete realization of something, namely the condition of the condition of solving the anti-self-dual equation it quite precisely is the real moment map type condition for being a stable homomorphic bundle. And so then if you think about you can think of those problems as in the category of stable holomorphic bundle over certain kinds. There will be some homes and next and so forth. But you might as well think of this term. So you don't need to think if you want to compute the x between two bundles, which is a useful thing to know, you might as well compute it here using just this complex. That will be contains exactly the same information. Make sense? Right, now the fixed points, which I promised to do. And so what is the so this is will we So again, suppose I have a general Nakajima variety. So it has some quiver V1, V2, whatever. 3 arrows to V3. Then you do a loop here, and then there's this W1, W2, W3. This is my frame quiver. Then there was an exercise how to find. So then if I take in GLW1, I'll take a maximal torus, maybe of the form maybe A1 through A dimension. Or dimension of W is literally called little wi. And similar for the other guys. Then the first exercise was to find the fixed points of this tori. Right? How do we find this? So this is Nakajima variety is a quotient. We mod out by the product. We take the cotangent of that, and we take the moment mapping, and we mod out by the products of GLBI. What does it mean? I have an action, a fixed point on action of the quotient. Means if I move a point, I can undo this motion by an element here, right? This means on the fixed point, it's just exactly like we had with the P1. So if I have a manifold, some bundles over it, that means over a fixed point, my group element starts acting on the fibers of the bundle over the fixed point. That means over a fixed point, this guy will start acting on all these VIs. Right? All of these VIs will be now graded by the action of my torus. Right? And since my torus only acts on the spaces, it doesn't act on any of the quiver data, then for this to be fixed point, the quiver data has to go from one weight space to the same weight space. Right? Means this torus acts on the VIs, and all the quiver maps have to preserve the weight spaces. Right? Means my quiver has to, if I slice them by weight space, there will be just copies of the same quiver. Is that clear? So this says that the fixed points of maximal or any torus, in fact, that sits on this GLWIs is a union of products of Nakajima varieties corresponding to the same quiver. That was one exercise. I hope you all did it. So I'm just reminding you how it goes. And so in particular, the quiver that of importance to Nikita's lecture, this quiver. So just V and W. I guess K and N or forgot what it was, something, just says that the fixed loci would be the product of the same guy when this is one-dimensional. And this is one-dimensional. Raise your hand if you know what the quiver variety is. Okay. And if you sit next to somebody who knows, so this in this case, so if this is Cn or maybe Ck, what was K for you? K. This is the Hilbert scheme of K points in C2, and its fixed points are parameterized by this kind of partitions, which you can. Raise your hand if you know that the Hilbert scheme of K points in the plane has something to do with partitions of size K. Okay, cool. So now we've established that. Now the tangent spaces you can compute. How are you going to? That was another exercise. Compute the tangent spaces. You can compute them from the actual geometry of the space. You can think, what are the actual axes? But you might as well compute it in this category. You can just compute it from just quivers, and get a result with arms and legs, I guess we should assign to there. So if I want to know, so what is it going to be? It's going to be if I compute the x between, so to compute the normal so in total, if this space is instead, if this space is R, right, for the remaining torus, right? There's a remaining torus that acts on this C2, this torus, yeah, that's right. And so the idea is that then if this is an R-dimensional space, and you have this quiver, this CK here, then the fixed points are R tuples of, the fixed points here are just products, R copies of this thing, and so then in particular, if we would take the combined fixed point of the R-dimensional torus and this torus T, then we're going to get an R tuple of partition of total size adding up to K. And if you want to know what's the tangent, if you want to know what is the normal space, all you need to compute is the x1 between one partition and another partition, which you can compute as shifts on, you can compute this x1 as shifts on C2, or you compute it as quiver, x1 as quiver representation using that just explicit description of the tangent space. Right, so this took all the time I had and 4 more minutes, and so maybe I'll stop here. So. Ну, прям вы, кстати,